Hello everyone. Let's analyze. So what does it mean to compute the slope of a curved function? Right, it makes perfect sense to compute the slope of a line, just rise over run. But what a strange question to ask, what is the slope of something curved? The same question can be posed, how do we compute the rate of change of a function when the rate of change, well, changes? Well, now that we have the power of function limits at our disposal, we can simplify our question to computing the slope of a secant, a line that intersects a function at 2 points, and then take the limit as the width of the secant goes to 0. Specifically, take the limit of the secant's slope. So here we have two pictures, and you might look at those two pictures and think, well, they look exactly the same. And that's because they are, but they're two different perspectives. In the left, we have a secant that passes through a function f at 2 points, x0 and x. We take the ratio of rise over run, that is slope of the secant line, and then we take the limit as x approaches x0. Of course, another perspective is to think of this in terms of perturbations. We have an x0, and then we perturb by some value h to f of x0 plus h. So here we have a secant that passes through f at x0 and x0 plus h. And of course we can take the slope of this secant because it's a line, it's just rise over run. And then we could take the limit as the perturbation h goes to 0. Again, when we do those two things, we're doing the exact same thing. We're just looking at it from two different perspectives. So we can take the perspective of the left plot by forming a secant slope function, f of x minus f of x0, that's rise, over x minus x0, run. So t of x is the slope, it's rise over run of my secant. It's rise over run of my secant. Again, as I mentioned, another perspective is to take the rise over run by looking at how x0 is perturbed by h. Indeed, this very idea of perturbing x0 and watching how f reacts to a perturbation is the very foundation behind stability analysis and chaos theory. Do small perturbations cause largely different outcomes? But for here, the two concepts are measuring the same thing. Let's take a look at an animated version of this picture so we can make sure that we understand this idea of taking secant slopes and the limit as the width of the secant goes to 0. So here we have some function evaluated at a and a perturbation of a, right? That is a plus h, and we drew a secant line between the 2 points. Of course, here h is fairly large. We see how big it is. It goes from here to here. But what happens when you take the limit as h goes to 0? Well, as h goes to 0, the secant line changes substantially, and the slope changes. But as h becomes 0, the secant becomes a tangent line. And when h is completely 0, we have exactly a tangent line. And the derivative is the slope of the tangent line. So now we're ready to give a formal definition of differentiable and the derivative. Let x not be an accumulation point of D, because we're taking a limit, and to take limits we need accumulation points. And let D be a domain of F. For each x in the domain not equal to x0, we'll define our secant slope function t of x, as we've already explained. Then the function f is differentiable at x0 if t of x has a limit at x0. And that limit would be the derivative of f at x naught, which we typically write f prime of x naught. Again, a equivalent definition, this from the perturbation perspective. Let x naught be an accumulation point of D, and f a mapping of D to R. Well, then for each non-zero h, for which x naught plus h remains in the domain, we can define q of h to be, well, again, our secant slope function, here as a function of our perturbation h. The function f is differentiable at x naught if q of h has a limit at 0. Again, we write this as the derivative. F prime of x naught is the limit as h approaches 0 of our secant slope function. Function that is differentiable at each point of a set is said to be differentiable on the set. So since we see that the derivative is essentially just a statement about a limit, specifically a limit of a secant slope, then we can actually use all of the machinery we've built regarding limits to apply to the derivative. So now that we have a robust and precise definition of the derivative, let's compute a derivative. Let's compute the derivative of f of x equals the absolute value of x, and demonstrate that this derivative doesn't exist when x is 0. Now again, you probably can look at f and you know already what the derivative is. This portion of the class, we're talking about an idea that's very familiar to you. The difference is that now we can be quite robust in our logic and saying specifically what the derivative is and has to be, and we can prove the result based on the definition. So recall the piecewise definition of the absolute value function. The absolute value of x is, well, itself if x is non-negative, and negative itself if x is negative. Well, let's consider 3 cases for x naught to determine whether the absolute value of x is differentiable at x naught, and if so, what is the derivative? So let's look at x naught greater than 0. Since x naught is greater than 0, then f of x naught is just x naught. And q of h, which is f of x naught plus h minus f of x naught over h, is just x naught plus h minus x naught. All right, we took the derivative off of here because x naught is positive. I'm sorry, we took the absolute value off of here because x naught is positive. But we can't take the absolute value off of here yet because we need to make sure that that's positive. Once you make sure that's positive, then it becomes quite simple. So our goal is to show that q of h has a limit at 0. Let epsilon be positive and let delta equal x naught. If we choose this delta, and if h minus 0, because 0 is where we're taking the limit, right, as h approaches 0, if h minus 0 is less than delta, then x naught plus h is greater than 0, right, because h would be sandwiched between delta and negative delta, which is x naught and negative x naught, right, because h is strictly bigger than negative x naught plus h is strictly bigger than 0. Therefore, the absolute value of x naught plus h is just x naught plus h. And our secant slope function just becomes h over h, which is 1. Now, if I take the limit, I just get 1. Because q of h minus 1 is 0, which is, of course, less than epsilon for any positive epsilon. Therefore, f prime of x naught equals 1 if x naught is positive. So case 2 is, of course, very similar. We choose delta to be the absolute value of x naught. If h minus 0 is less than delta, then q of h minus negative 1 is equal to 0, less than epsilon. So we get that the derivative of f at x naught for negative x naught is negative 1. Now, at x not equals to 0. At x not equals to 0, what we will show that t of x does not have a limit. Actually, we'll show that q of h doesn't have a limit by showing that it does have a right-hand limit and a left-hand limit, but the right-hand limit and the left-hand limit do not agree. In fact, this might recall to mind a certain midterm question you saw recently. The limit from the right is 1 because f of 0 plus h, when h is positive, is just h. So h minus 0 over h is 1. And if h is negative, that is to the left of 0, then f of 0 plus h minus f of 0 is a negative h. Over h, I get negative 1. So the limit from the right is 1, but from the left is negative 1, and they don't agree, meaning the limit at x equals 0 does not exist. Therefore, f is not differentiable at x not equals 0. So here we have a plot of f of x equals the absolute value of x and its derivative there in red. Let's look at one more example since we're all here. Suppose f of x equals x times sine of x for non-zero x, and f of x is 0 when x is 0. So here f is defined for all x. F is a mapping from R to R. Show that f is not differentiable at 0. Well, to show that f is not differentiable at x equals 0, we need to show that the limit as h approaches 0 of f of 0 plus h minus f of 0 over h doesn't exist. Well, what we're going to show is that this actually reduces to a problem we've already worked out, because that equals the limit as h approaches 0 of h times sine of 1 over h divided by h. My h's cancel, and I'm just taking the limit as h approaches 0 of sine of 1 over h. And that limit does not exist. We know it doesn't exist because we showed that it doesn't exist in lecture 13. There was even a beautiful picture of why it doesn't exist. So I would encourage you to revisit that portion of lecture 13 to make sure that it's crystal clear why the limit as h approaches 0 of sine of 1 over h does not exist. Well, that's it for today.